Hello, this is Mr. Wynn, and this video is about nth roots and rational exponents. So far, we worked a lot with square roots. Now we're going to move on to third roots, fourth roots, fifth roots, and nth roots, where n is just a number. So if n was 5, that'd be a fifth root. If n was 2, it'd be a square root. If n is 4, it'd be a fourth root. So the only difference is that little number outside the root or radical sign, and that number is called the index, and it is a very important number. It tells you how many we need for a complete group. So a reminder, when simplifying radicals or roots, if the answer isn't obvious, we can and should always use the factoring tree branch method. So for square root of 64, technically there's a 2 right here. That's the index for square roots, but we use square root so often, we stopped writing that. It's become the default. We need pairs, 2 of a kind. So I can do the tree branch. I can say this is 8 and 8, and technically I could stop there because that's a pair. So we know the square root of 64 is 8, and there's plus or minus, but I'll leave it like that. If I do the cube root of 64, it's not so obvious. So I'm going to do the tree branch. I know it's 8 and 8, but that's not a pair. So I'm going to break it down to 4 and 2, 4 and 2. And then these 4s turn to 2s. I find groups of 3. So not pairs, but triples. Here's a triple. Here's a triple. So remember, groups go outside. 2 goes out. Another 2 goes out. There's nothing left over inside. So you multiply it, you get 4. 4 is the cube root of 64. If I do the fourth root of 64, same idea, but I need 4 of a kind. So I'm going to try that. So let's do 8 and 8 again. 8 is 4 and 2. 8 is 4 and 2. 4 is 2 and 2. 2 and 2. I need 4 of a kind. So here's 4 of a kind. Here's a group. For groups, 1 goes out. These last 2 2s have no pair, or not pairs, but 4 of a kind, so they stay inside. And you must put this index 4 because this is different than square root. The 2 2s stay inside. You multiply it. Find out is 2 fourth root of 4. That is the fourth root of 64. So n can be any number. It just tells you how big your group is. All right. Remember, some numbers have more than one real nth root. For example, 64 has square roots of 8 and negative 8 because 8 squared 64, negative 8 squared 64. We call the positive one the principal root, and sometimes depending on the problem, they want just the principal root, the positive one, so the negative one, sometimes they want both. So check what they want. If they just have nothing in front, they just want the positive. If they have a negative in front, they want the negative. If they have a plus or minus in front, they want both. All right. So simplify the following. Square root of 16y to the fourth is invisible 2 here, but I'll put it there just in case. I break it down. 16 is 4 and 4, and just go a little further, 2 and 2. I have a pair, so 2 2s go out. There's no numbers left over, so the square root doesn't happen here. Same thing for the letters, y's. There's, if I break it down, that's actually 4 y's. Y. I circle pairs of y. Here's a pair. So 2 y's go out, nothing stays inside. Multiplying together, 2 times 2 is 4, y times y is y squared. Alright, so y'all know the square root of 16y to the fourth is 4y squared. Over here, the fifth root of 243, a to 20th, b to 25th. I'm going to break down tree branch. It's 3 and 81. 81 is 9 times 9. That's 3 times 3. That's 3 times 3. 5 of a kind. Here's 5 of a kind. So there's a 3 goes out. There's no number left over. A to 20th. I could write 20 A's, but it takes a while. So I'm going to just think in my head, how many complete groups of 5 A's would I have? You actually just divide. 20 divided by 5 is 4. It means 4 complete A's that come out. So I'll just put A to the fourth power. No A's remaining inside. Then B to the 25th. There's 5 groups of 5 there. So 5 B's will go out. There's no B's left over. That's your final answer here. Alright, there's a tricky type of problem called the even odd case. And that is basically if there's a variable inside that has an even exponent and the index is even and it comes out with an odd exponent, so that's even odd, then you must use absolute value signs around the variable. So for this problem, the fourth root of y to the fourth, well, you know there's 4 y's. 1, 2, 3, 4. I used to divide. Remember, that's the faster way. But I need groups of 4. Here's 4. Y comes out. There's some left inside. So y comes out with a positive 1 exponent. Alright, so inside was even, 4. Here's the even. Index was even. There's other even. And here's the odd. If it is even, odd, you must put absolute value around the letter in your final answer. Final answer is absolute value y. The reason we put it there is because we don't know what y is. Because inside, say the inside was 16. We know 16 is actually equal to 2 to the fourth power. So y could have been positive 2. But we know 16 is also negative 2 to the 4th power. So y could have been positive 2 or negative. We don't know. So we put the absolute value sign to be extra safe and just say it'll turn to a positive. All right, over here, same idea. Square root of 36y to 3rd power. We know that's 6 and 6, and that's a shortcut, so I'll use that. So 6 comes out. There's 6 y's. We're doing pairs. I divide. 6 by 2 is 3. 3 full pairs. 3 groups come out. Nothing left over. Even, odd is 3. So I have to put absolute values around that letter. That's the final answer there. Alright, so now that you understand what an nth root is, you can figure out rational exponents, as they're just more complicated versions of nth roots. A reminder is rational numbers are just fractions. So we will now simplify problems with fractional exponents, and keep in mind that all the exponent rules we learned still apply. So know how to add, subtract, and multiply exponents when you're allowed to do that. The formula is this. When you have a base a to a fraction exponent m over n, we can rewrite that as a radical as the nth root of a to the mth power. Alright, so here's how I remember it. The base and the top of the fraction stay together. So a to m, a to m. The denominator, so here's a, here's m. The denominator, this n, is the index. It goes on the outside of the root sign. Like an exponential form is there's an exponent in the problem. Radical form is there's a radical, a root sign in the problem. So the first one says, what is 4 to 1/2 power? Remember, we gotta learn powers as, like, if you had 4 squared, it's 4 times itself twice. But what's it mean to have 4 to 1/2? What's 4 times itself? 0.5 times. Or the second one, what's 4 to 3/2? 3 over 2 is 1.5. What's 4 times itself? 1/2 times. Doesn't make sense. That's why we use this formula. We're gonna rewrite that. This will be written as 4, the 1 stays with it, and outside will be 2. This is just square root of 4. Well, square root of 4 is just 2. And I could type that in calculator and it'll be true. Over here, what's 4 to 3/2 power? So that's 4, the 3 stays with it, that's the numerator, and the outside is 2. So 4 to 3/2 is the same as square root of 4 to the 3rd power. Now you have two options, and there's a tip. You can root first, then power second, or you can power first, then root second. I would rather root first to keep the number small, and then do the power. Because if you do the power first, it's 4, for example, 4 cubed is 64. Squared 64 isn't too bad, but if it was a bigger number, it'd be a pain to do the square root of. I can square root 4 because it's easy to find pairs, and then cube that. So I'm going to square root of 4, which is 2. Then this 3 comes out. Well, that's the exponent stays. Then 2 to the 3rd power is 8. That's the answer here. All right, so let me type that in. So it was 4 exponent fraction 3 over 2. We don't know what that means, but it's 8. So 4 to the 1.5 power is 8. All right, my other option would be to what's called square a power first. So it's 2. I work on the inside. 4 times 4 times 4 is 64. Then I work on that, which also gives me 8. Right. So your choice. Again, I'd rather root first, power second. That's why I underlined that. Alright, so now rewrite each into radical form, but do not simplify. So right now it's exponential form. Change them to the root stuff. So let's see, 3 is the base, 4 stays with it, outside would be a 3. Here, C is the base, 5 stays with it, the outside would have 6 for index. Over here, be very careful. That 9 over 2 is for x only, not for 4. Otherwise, I have parentheses like this right here. That's parentheses is very important. Alright, so that's like 4 times x to the 9 over 2. So this would be 4 times the radical. X, 9 stays with it, 2 on the outside. 4 times the square root of x to the 9th. This next one, the exponent goes to both 3 and k because it's parentheses. Remember, if it's one term, the exponent goes to everything inside. So I can say that is radical, 7 on the outside. 3k has the cube that stays on the inside. So numerator on the inside, denominator is the index on the outside. Alright, bottom's the reverse. Rewrite each of these. So remember, the inside was the numerator, the index, and the outside is the denominator. That's it there. This one, be careful, there's missing, it's invisible 1. So numerator is 1, denominator is 4. Here, be careful. Remember that 7 is only for h, not for 5. So I have to do it separately. This 5 has a 1. So this is 5 to the 1/3 times h to the 7 over 3. Again, whatever's inside stays on top, stays with the number or letter. It's the numerator. The outside, the index, is the denominator. Now this one, this hj, has it squared together. So it stays together, hj. The numerator is 2, the denominator is 9. Alright, when simplifying a problem, you can use either form you want, since they both give you the same correct answer. Get comfortable working with both. A problem might be easier in radical form if you like doing the tree branch. A problem might be easier in exponential form if you know exponent rules. You're even allowed to switch forms in the middle of a problem. Sometimes you use a combination, like you'll see in a second. So first one, evaluate 81 to the negative 1/4 power. So first, you know negative exponents, we can make positive. I put this over 1 and move to the bottom. I can say that is 1 over 81 to the 1/4. From here, some people like saying radical. That is 81. The 1 stays inside it, the 4 goes outside it. Alright, the 4 through to 81. I'll go over here. 4 through 81 says break it down, find 4 of a kind. That's 9 and 9. That's 3 and 3. That's 3 and 3. Find 4 of a kind. There goes 4. 3 goes out, nothing stays inside. So this turns into 1 over 3. That's your final answer. That's one way. Another way would be this. From this step here, I can say 81 is the same thing as 9 squared. I can use my exponent rules here. So I can multiply the exponent 1/4 to the exponent 2 to get 1 over 9 to the 1/2. I could change the radical here, or I could say, and this is a nice trick, 9 is 3 squared. So 3 squared to the 1/2, I can multiply 1/2 times 2 is 1, so I get 1/3. You'll see this trick used more often in the next problem. But your choice, you can keep in radicals, or you can do exponential form. This one, let's do it the old way. This is the key root of this. I can do breakdown tree branch, 8 and 8, 4, 2, 4, 2, 2, 2, 2, 2. Here's a triple, 2 times 2 goes out. No numbers in, z to the 6. How many groups or 3 triples in there? Or this 2? Alright, z squared comes out, nothing else. This is 4z squared. That's the answer there. Or I could do this. This is 64 z to the 6 all to the 1/3 power, because that's the cube root. I can change 64 into 4 to the 3rd power, z to 6. This, because there's a 1 term on the inside, I'm allowed to distribute the exponents to other exponents. So this would be 4 to the 3 over 3, z to the 6 over 3. I can reduce that. 3 divided 3 is 1, 6 divided 3 is 2. Same answer. So again, get comfortable with either form. You can keep in radical form, do the tree branch stuff, or you can keep in exponential form and do exponent rules. Last problem is kind of complicated. Alright, here you have to use a combination. So first it says find the 4 through to 27 over the square root of 3. I cannot divide those are different radicals. So I'm going to change the first one into 27 to the 1/4 power, and the bottom one into 3 to the 1/2 power. I'm not allowed to divide those because they're on the same bases. So I'm going to use some tricks and change 27. We know 27 is 3 to the 3rd power. So I did not change, it's still 27 to the 1/4 over 3 to the 1/2. I can do, for the top, I can multiply as exponents, that's power to the power, because the inside is only 1 term. So 3 times 1/4 is 3/4 over 3 to 1/2. Now the bases are the same. This is like saying x to the 10 divided by x to the 3, where you subtract exponents. So 3 to that power divided 3 to the other power, you can subtract. So I'm going to do 3 over 4 minus 1 over 2. I need common denominator, so I'll times by 2 over 2 to make it 3 over 4 minus 2 over 4, which is positive 1 over 4. So this will finally turn into 3 to the positive 1 over 4. That's the answer. If you want to make that a radical, you could say that is 3, 1 stays with it, 4 on the outside. Those are the exact same answer, just different forms. One's exponential form, one's radical form. And there actually is a way to do the whole problem in radical, but it's easier if you use exponential. That's the whole video. Thanks for watching. See you in class. Bye.